All right, welcome to lesson 3. Today we'll be talking about enthalpy. Just a little reminder about the schedule. We have lessons 1 through 3. That's from this first week of classes. Next week in the Zoom session, we'll be having office hours. Next week, all the homeworks 1 through 3 are due, including the one for this lesson, which is due Friday, April 17th at midnight. Okay, a little bit of a review. From lesson 2, we talked about calorimetry. And calorimetry is all about figuring out the heat associated with different reactions. We talked about a couple of these types of reactions: combustion, vaporization, and dissolution or solution. They have the same meaning. And so we can figure out the energy or heat associated with these. We had some key equations, right? So we can find the heat for a calorimeter based on C times mass times delta T. And then in a calorimeter, Q of a reaction equals negative Q of the surroundings. And the surroundings, that's the calorimeter itself, the water. Okay, one other review, and this is from 215, but we're going to be using it today through the rest of this quarter, and then also through all of chemistry. And that's converting grams, in this case water, to moles. So let's remember, how we have to do this is we need to know something called the molar mass. The molar mass of water, H2O, is found by taking 2 times 1.008, that's for hydrogen, plus the molar mass of oxygen, and that is going to get me the molar mass of H2O. I can then use this value to convert from grams to moles. In this case, I divide because that's grams over moles, so that's going to cancel out the grams and leave me with moles. All right, so we've been talking about thermochemistry. Now we're going to move into other types of energy, and this is what we call thermodynamics. We're going to continue up, finish up chapter 5, and then move to 16. And let's remember the first law of thermodynamics that we talked about, and that's that delta U, the internal energy of a system, is equal to the heat flow, which is Q, plus W, which is work. So delta U equals Q plus W. All right, now we should talk about why we're talking about delta U and not just U. U is internal energy. But U is what we call a state function. State functions are properties of a system based solely on its current state. So, for instance, let's say I go from base camp up to the summit of Mount Kilimanjaro in a straight path. Someone else goes a longer way. At the end, if we were going to say, hey, what's our altitude? We're going to have the same altitude. That's what we call a state function. But if we were to say, hey, what's the distance traveled? This person Y is going to have to take a longer route, a longest distance traveled than person X, me. So state functions are things that don't depend on how we got there, just that case. And these are things like U, internal energy, and what we're going to talk about today, which is enthalpy. And these are hard to measure. Think about it. You know, if I'm on the top of that mountain, I go, what's my altitude? I don't know. But if I were to say, hey, what's the distance traveled? I could say, hey, here's my iPhone. It says I traveled this far, right? And so path functions, which depend on where we start and finish, these are easier to measure. And these are things that like heat and work and anything that has a delta, right? Delta, again, remember that means change. So a change in internal energy is much easier to measure. Okay, so let's talk about that term we just talked about, enthalpy. So enthalpy is H, and H is the state function dependent on a system's internal energy, pressure, and volume. So H is equal to U plus P times V, where P and V are pressure and volume. Enthalpy is really hard to measure. Okay? But if I look at the change in enthalpy and I keep constant P, that means I have delta H equals delta U plus P delta V. Now, earlier we talked about expansion work, And we said that work is equal to negative P delta V. So I can plug this in, and I get that, and because delta U equals Q plus W, I can rearrange this, and I can get that delta H equals Q, or heat. How we get here isn't that important, but all we need to know is that enthalpy, or delta H, is just a fancy word for heat, as long as we're at constant pressure. Just remember that pressure constant, that's when we have an open atmosphere, right? Anything like a burning candle, that would be constant pressure, right? The room pressure is not changing. But if we had something like a bomb calorimeter from last time, which is a small container, that would not have a constant pressure. That would have a constant volume. Okay? So this coffee cup calorimeter, this would be constant P, but this would not. Okay? All right, so delta H is heat. And we can call it either enthalpy of reaction or heat of reaction. We're going to use both terms, so you should be able to use both depending on what it is. So enthalpy, heat, they're the same thing. Okay, so let's say we have a system here. This is our reaction, A plus B going to 2C. If I look at the periodic table, there's no A and there is a B and a C, but this isn't about carbon and boron, right? This is just any reaction. I'm doing a generic reaction. Okay, so we have some rules about delta H. The first rule is that a lot of times we go ahead and we say, here's my reaction, and I just say, hey, its delta H is negative 572 kilojoules. Well, that, we can just list all these. That delta H tells me whether it's exothermic, meaning it's negative, or endothermic, meaning it's positive. If it's exothermic, that means heat is a product. So a negative value means it is being produced. A positive value, like down here, means that heat is required for that reaction to occur. So let's think about it. What's a type of reaction that has a negative delta H? Heat. Combustion, right? Burning stuff. Burning stuff produces heat. That's why we do it. So this, right, we'd have a negative value for anything like combustion. All right, one other thing, one other rule, rule number 3 is if you switch the direction of reactants, and products, you switch the sign. So for instance, A plus B goes to 2C. That has delta H of negative 572 kilojoules. But if I reverse it, so now 2C is my reactants, my delta H is going to be positive 572 kilojoules. Okay, another rule is if I multiply a reaction by some factor, that delta H also gets multiplied. So if I said A plus B goes to 2C, and that's negative 572 kilojoules, if I reduce everything by half, so I have half A plus half B goes to C, my delta H is half as much. Okay? This is the same as if, hey, I have 1 log on the fire, I'm going to get this much heat. If I put 2 logs on the fire, I'll get twice as much. If I only had 1, I'd have half as much. Okay? And if I were to double it, so here's half. If I were to double it to 2A plus 2B, I would get twice as much. So negative 1144. All right, one last rule with delta H's are that it's dependent on the physical states. So for instance, if I have this reaction, 2H2 plus O2 going to 2 liquid waters, that's going to have this delta H. And if it goes to gas, it's going to have a different delta H. This kind of makes sense because I know that liquid water and gaseous water are different. In fact, to go from liquid water to gaseous water, I actually have to put heat into the system. Okay. All right, so let's use our delta H in a video problem. All right, so here's a problem. We're told two H2Os going to 2H2 plus O2. I tell you that delta H equals 572 kilojoules. What that means is for every 2 moles of H2O, I get 572 kilojoules. What if I had 4 moles of H2O? I would get twice as much. If I had only 1 mole H2O, I'd get half as much. I get 286 kilojoules. So what I want to do is, in this case, I only have 25 grams. So I have 25 grams of liquid water. I want to know how much heat I'm going to get out. So the first, or how much heat is required. So the first thing I have to do is convert from grams water to moles water, and then I can use that to figure out how much heat I'm going to get. Okay, so this is a video practice. You can go ahead and do it on your own. We're going to do a different problem. All right, so in this problem, we have 25 grams of NaOH. That's sodium hydroxide. That's a base we talked about in Gen Chem 1. And it's dissolved in water with excess HCl. This produces 36.25 kilojoules of heat. And we're asked what's the enthalpy change per mole of NaCl produced. Okay, so enthalpy change, remember that's delta H. Okay, so we're told we have HCl plus NaOH going to NaCl plus H2O. All right, so what we want to do is we want to figure out, hey, what's my delta H per mole of NaCl? So what we need to do is we need to realize, and we know Q, we know how much we already have. Heat, we're told 36.25 kilojoules. We need to figure out how many moles of NaCl. And here's where we have to remember something else from Gen Chem 1. And that's that stoichiometry is important. So let's say we have 25 grams of NaOH. We're told here that we have excess HCl. So if I have excess HCl, that means that NaOH is my limiting reactant. So I can use this 25 grams NaOH to figure out how much NaCl is going to get produced. All right, so I go ahead. I convert first from grams NaOH to moles NaOH. I can figure out the molar mass of NaOH based on the periodic table. So it's 39.997 grams is 1 mole NaOH. I get this from 22.99 plus 15.999 plus 1.008, the molar masses. And that'll get me the moles NaOH. Now, I want to know moles NaCl, so I can just say for every 1 mole NaOH, I get 1 mole NaCl. And that's going to get me 25 divided by 39.99 or 997. That's going to get me 0.625 moles NaCl. All right, now this value, that goes there. So I can find delta H equals 36.25 kilojoules over 0.625, and that's going to get me negative or 58.0 kilojoules per mole. And there's one last trick, and that is that, notice that it says it produces heat. Right? Producing heat means that up here, heat is a product. And so that means that my delta H here is negative. Okay. So let's look at this one more time. I want delta H per mole NaCl. So I can take Q over moles. So I need to use my stoichiometry to do that. And then I plug that in. And now I say it's produced. That means that it's giving off heat. What does that mean? If I were to do this reaction in a cup, right, that cup's going to get hot. Right? It's giving off heat to its surroundings. Okay, so delta H's are useful. Because knowing delta H's, I can actually go ahead and I can take those delta H's for a bunch of reactions and I could put them in a table. Or in today's age, they'd be on some website, right? So you can see here that there are a bunch of reactions here and they're different delta H's. Okay? You can see that these are all negative, so these are all exothermic. And one thing is important, it's always important to compare reactions under the same conditions. Because if you have different conditions, you can have different variables. So what we often do is we compare reactions at what we call standard state. Standard state is pressure of 1 atmosphere. If I have something like where it's aqueous, it'll be 1 molar. And then typically it's 25 degrees. And when we do this, we use this right here, this little circle here, which we call naught. So if I wanted to write this out, I would call it delta, that's for the triangle, H naught. That means it's under standard conditions. If it's not under standard conditions, I don't include that little circle there. Now, in the book, just for other clarification, they include this 298. And that means that it's at 25 degrees C. But usually in this class, we won't do it. All right, so here are a bunch of delta H's under standard conditions. They're in kilojoules per mole, and you can have them all listed. Okay. These ones that are on the list are what we call delta HC. Delta HC is the standard enthalpy of combustion or heat of combustion. Remember, heat and enthalpy, they mean the same thing. So this is the enthalpy change when 1 mole of a substance burns under standard conditions. So we call this heat of combustion. Now the thing is, delta HC is always negative. It's always negative because burning stuff always is negative, or it always produces heat. All right, so here, for instance, is the delta H for the burning or the combustion of methane. You can see that we have CH4 plus 2O2 going to CO2 and 2H2O. This means that I have negative 890.8 kilojoules for every 1 mole of CH4. All right, so I can have all these delta HCs for a bunch of different reactions. Some of these are hydrocarbons, some are non-hydrocarbons. You can see here, these are all hydrocarbons, some with oxygen, and then these are non-hydrocarbons up here. The physical state matters. If I burn something in the liquid form, it's different than if it's in the gas form. Notice they're all negative because I'm all burning things. And notice one other thing. A lot of these have fractions. And that's because when we deal with delta HCs, heats of combustion, it's always for 1 mole of a substance. So what that means is, look at this one in the front. There's never any exponent here. So this is always per 1. So it's okay to have that fraction on everything else because we only want it per 1 mole of whatever we're burning. So let's use a heat of combustion in a problem. Now, heats of combustions are important, or that they're useful, because a lot of times we compare different types of fuel and things we burn. So let's say we're burning gasoline, and we burn 1 gallon of gasoline, and we want to know how much heat we're going to produce. Gasoline, obviously, we're burning, probably a couple gallons at least every day, getting into school and out of school, if we're driving, that is. So what we're going to do is we're going to use this delta HC that's provided for octane, or for octane, which is what we're going to assume it is. And we're going to use this in order to figure out how much heat we get when we burn 1 gallon of gasoline. All right, so let's start off by coming up with a plan. Right? So we're told delta H is negative 54.61 kilojoules per mole. And remember that delta H is always Q over moles. So what are we asking for in this problem? We're asking for the amount of heat. So we're asking for Q. So I can find Q by just rearranging it. So if I take a delta H times mole, the number of moles I burn, that's going to give me my amount of heat. All right, so we know delta H, so all we need to know is the moles of octane. We're not given moles of octane, and we're not given grams of octane like we talked about earlier, but instead, we're given 1 gallon of gas, or octane. I already told you what this is, 3.785 liters of gasoline. Okay, so we need to go from liters to moles. So what do? Well, we can go from liters to milliliters, milliliters to grams, and then from grams to moles. Why do we go this route? Because we know how to go grams to moles, right? And we know that if we know a volume, we can get to grams based on the density. And that's given to us here. All right, so we're going to do this. So we have 3.785 liters. For every 1 liter, we have 1,000 mLs. That cancels out the liters. Then we get 0.692 grams for every 1 ml. So that's going to give us the amount of grams. This ends up being 2,619.22 grams. I'm going to go ahead and leave some extra because I'm not at my final answer yet. So I can take this, 2,619.22 grams, then say, how many grams are in 1 mole for octane? This is C8H18. Well, the molar mass of C8H18, I was given to it, but I could have found it from the periodic table. It's 114.23 grams. And so this ends up being 22.92 moles of my octane. So I know how many grams I have, or how much heat I get per 1 mole. Well, I have this many moles, so all I have to do is multiply. It's like if I go to the store and they say, hey, it's $1.25 per avocado. If I get 2 avocados, it's $1.25 times 2. Okay? So I take this negative 5461 kilojoules per mole, multiply it by 22.92 moles, and that's going to get me my final value, which is 125,000 kilojoules. It's negative here because it's producing it. All right, now notice I burn 1 gallon of gasoline if I go about 30 miles. I'm producing a lot of heat. That's why we do it, because burning that octane gives us a lot of heat, a lot of energy, and that's what drives our car. Okay, so again, we converted from liters to grams, and then from grams to moles using the molar mass. And once I knew that, I could figure out the kilojoules. Notice here it gave me negative, which just means it's produced. Okay, so we talked about using delta H. Let's go ahead and have you guys figure out what the reaction is for burning octane. So I have C8H18. And it's liquid. Figure out the reaction for burning this octane. Let's remember back to 215. What is burning? It's reacting things with oxygen to form CO2 and water. I told you I'd get better at this. All right, so, maybe it's better. Who knows? So I'm going to go ahead and do this. But remember, this isn't balanced, so I need to make sure to balance it. And remember, heat of combustion is per 1 mole of that octane. All right, so you can see that video later if you want. All right, the last topic we're going to talk about is standard enthalpy of formation, or delta HF. And remember, it's standard, so that just means under standard conditions, one atmosphere pressure, 298 K. So we have a delta here, or a knot here. All right, so combustion is what you get from burning something. Delta HF is the enthalpy change when 1 mole of substance is formed from its elements in their most stable state. Okay, so this is, hey, taking to get all these things and putting them together. All right. So let's say I tell you that the delta HF for CO is negative 110.5 kilojoules per mole. So what does that mean? Well, I'm going to create 1 mole of CO. That means it's my product, right? If I'm forming something, that means it's my product. So I'm going to make CO. What do I make CO from? Do I make CO from boron and from argon and from hydrogen? No, I make CO from carbon and oxygen. That's how atoms work. So I'm going to take carbon and oxygen, and I'm going to make those into CO. But this part here that says in their most stable states, what this means is if I have just carbon in nature by itself is typically just a solid. It's actually graphite, what you use in pencils, not diamond, which is another form of carbon. And oxygen, in its most stable state, is O2, gas. And so these are under standard conditions, 1 atmosphere at 298.15 Kelvin. So it's making CO from carbon and oxygen in their most stable state, which are carbon solid and O2 gas. Now, if I look at this, something's wrong, and that's that, it's not balanced. So I need to balance it by going ahead and saying that, all right, I have 2 oxygens on this side. I only have 1 oxygen here. So I'm going to put a half in front of this O2. That's going to get me 1 oxygen. It's okay to have fractions in this case. Why is it okay to have fractions? Because it says per 1 mole of the product. Not 2 moles, 1 mole. All right, so here's my reaction. Notice I put that heat as a product because it's being produced. It's negative 110.5 kilojoules per mole. All right, so we said stable states. What does that mean? Hey, we need to look and we need to figure out what the stable states for everything is. Right? All right, so for most elements, their most stable state is as a monatomic solid. What does that mean? Mono means 1, atomic mean atom, so 1 atom of that solid. So carbon solid or sodium solid or arsenic solid. Some are a little weird. Sulfur is actually S8, so 8 sulfurs bonded together, but as a solid. Your noble gases, remember that's helium on down, those are just monatomic gases. That just means helium by itself and neon by itself. Gases, I should have on there. And then some are diatomic. These 5 right here, hydrogen, fluorine, chlorine, nitrogen, and oxygen, these are gases. So H2, N2, O2, Cl2, and F2. These are ones we used a lot in the gas chapter. Right? Br is actually a liquid. It's Br2 liquid. And then iodine is I2 solid. By the way, the reason why fluorine, chlorine, bromine, and iodine all form 2 is by making that bond, we can get all those halogens an octet, if we think back to 215. Okay, so let's do one problem together, and then you'll do some yourself. Let's go ahead and figure out the heat of formation for, or that the chemical equation representing the heat of formation for N2O5 gas. All right, so I'm told I'm forming N2O5. So that means it's my product. So I'm going to form N2O5 gas. What do I form N2O5 from? Do I form it from argon and neon and all these things? No, from nitrogen and oxygen. But nitrogen in the environment isn't there as nitrogen. It's as N2 gas. And oxygen is an O by itself. It's O2 gas. Right? So I have N2 plus O2 going to N2O5. That is my equation, but it's not balanced, so I need to balance it. Notice I have 2 nitrogens here, 2 here. I have 2 oxygens here, 5 oxygens here. So I need to put something in front of there. Well, if I put a 2 in front of here, that's going to get me 4. That's not enough. If I put a 3 in front of there, that's going to get me 6. That's too much. So between 2, 2's too little, 3's too much, so 2.5 or 5 halves we'll put in front. So now I have 5 oxygens. Okay. This is my equation. I do not do what I did in 215 in Gen Chem 1. In Gen Chem 1, I went ahead and I doubled this. And I do this. I don't do that here because look at that at the top of the screen, 1 mole of a substance, right? I want 1 here. I don't want 2. Okay, that is delta HF for N2O5. Why don't you do it for some other ones? Okay? So in video problem 3C, you're going to do it for C2H5OH, that's ethanol. You're going to do it for O2, and then you're going to figure out the delta HF for O2. I'll actually give you a hint. The delta HF for O2 is 0. Why is it 0? Because O2, if I make O2 from something, I'm just going to make it from O2. So I'm making O2 from O2. That's not a reaction. So my delta H is going to be 0. We'll explain that more in the video. Okay, so I can take all these delta HFs, I can collect them. So you can see here are a bunch of delta H's for HFs for a bunch of different compounds. There's some other things. We'll explain these next week. Not right now. That's too complicated for right now. Notice some are positive, some are negative, right? And some are 0. Whenever I have an element in its stable state, in its free state, that's 0. So aluminum solid is its free element. Antimony solid, that's 0 as well. Okay, so we've talked about standard enthalpy of combustion, standard enthalpy of formation. We also have other ones, standard enthalpy of solution, standard enthalpy of vaporization. You know, these are all per 1 mole, in this case being dissolved, in this case vaporizing. Okay, so that is it for enthalpy. So remember that delta U equals Q plus W, and from that, we got that delta H is Q. This is a biggie, right? Delta H is heat. Okay? And then we talked about some different types, combustion and formation being the big ones in this section. And last thing I'll say, remember this knot means it's at standard conditions or standard state. That's 1 atmosphere, 1 molar, 298.15 K, or 25 degrees C. And usually they're in kilojoules per mole. So if I know how many moles, I can just multiply them out and get kilojoules. All right, I lied. There's one other thing I wanted to say. The signs of all these variables are going to become really important. And it's going to become more complicated next week. So I just wanted to think. So remember, delta U is internal energy change. Right? If it's positive, that means it's gaining energy. Negative, losing energy. Q is heat. So positive means something gets heated, right? I put it on the stove. That's a positive Q. Negative means it's cooling. I take that glass and I put it in the freezer. That's a negative Q. W is doing work, right? So if it does work, so if I, the system, do work, that means it's negative. If work gets done on me, that means it's positive. And then delta H, we said, is enthalpy change. Positive means endothermic. Negative is exothermic. What's the type of exothermic reaction? Combustion. All right, so that's it for lesson 3. Go work through the worksheet, watch that video, do the homework. Talk to you later. Stay safe.